So we really need to understand how to work with rebars. Rebars comes in different length, and usually your beam is gonna be, in many cases, gonna be longer than the bar length, and maybe you need to splice it. The way that you splice it, we have a few methods. Splice can be mechanical, can be by welding. Let's say that you have here two rebars and you can just weld them to each other. This can be this what you call here butt welding, or it can be lab welding. Then you weld the rebar in here. This give you one way of splicing the bars. Sometimes also we have coupling, and the coupling is gonna be maybe threaded or maybe by compression, and you can use it to splice a bar to provide the continuity. The easiest way that people like to use in construction is gonna be just to lap splice it. Lap splice it, which means just put the rebar next to each other and that's it. No welding required. But now the length should be enough to be able to take the force out of the rebar to the surrounding concrete and then back to the other rebar that you're trying to splice it with. In general, we assume that beams are simply supported. So when you have a beam like the one that you see here, by any chance, is my screen clear? Hello? Do you guys see my screen? Okay, yes. Very good.
Yeah, yes.
So usually we assume that this can be the beam, and then you have simply support here like a hinge and a hinge on both sides of the beam. But in reality, this rebars kind of going to the top, and the top usually is going to be bent inside the column. This provides here some continuity, meaning that a beam like this is going to be supporting positive moment at the middle and negative moment at the top. In simply supported beams, we assume that moment here is going to be equal to 0. But according to the way that you build it, I mean, the way that you build beams and columns, performance is going to be different from what you assume. You assume it's going to be hinge. Reality, you're going to have certain fixity here at the end. Look what happened when you load the beam. Column is not going to stay vertical because here you are cranking some moment to it, which means here you're going to have tension. The tension here is going to be in the middle, right? And then you're going to have another tension in the column. Because now this column, we provide fixity to the beam itself. So we assume certain performance and certain assumptions on the beam. Reality is going to be different because it depends on the way you build it. If you build this construction here to be monolithic, then you bring the beam bars and you drop it down inside the column, you're going to be here resisting deflection and rotation of this beam. You're going to be building here some moment at both sides of the beam. When you assume that, let's say, again, I'm going to go back here to the simple beam assumption. If you have here a simple beam assumption, you assume here that the moment is going to be equal to 0 at the bottom of the beam, and also the moment here is going to be 0, it's going to be maxed out here. Other question is, if I need here, let's say 4 bars at this point, how many rebars do I need here? In the standard construction, you just keep the rebars, like the 4 rebars is 3. But let's say you decide here that you'd like to save the rebars. Then you come back and say, at this location, I need the 4 rebars. At this location, I just need 2. Theoretically, at this location, I need nothing. Why you don't need anything? Because moment is going to be equal to 0. But you cannot do this. You need to have at least a couple of rebars going through. So if I like here to put the rebars, I'm going to go back here to this slide. I'm going to say, here are few rebars. It's going to be straight, like 2 rebars minimum, and some rebars either that I can bend it and bring it up to use it, or I can just stop it. If you want to stop the rebar here, this is fine. But you need to do some calculations. You need to know exactly where to stop the rebar. According to the moment diagram, if I may draw here, let's say here's the moment diagram. According to this moment diagram, moment here is maxed out. And again, moment here is going to be equal to 0. And moment here, let's say, is going to be somewhere in between. Let's say in a given beam design, I need here 4 rebars. We say here I need 4. And here I may need 2 rebars, not just 4. And here I need nothing. It's going to be 0 rebars. But I can't do this. I need to keep at least 2. One of the options I can do is to bring 2 rebars and running it straight from the beginning to the end. So I'm going to come next to it. I'm going to say, here we go. Let's see with this arrow. I'm going to say, we have here 2 rebars. This 2 rebars can be running straight from the beginning to the end. Then bring another 2 rebars and running from here to there. Let's give you another 2 rebars. And I'm going to set them next to each other. So in reality, this is going to be covering this. It's going to be like this, very close to each other. Actually, they're on the same level. Now, at the end, when you look at this section here, how many rebars have I provided? You're going to say, well, you provided here 2 in one layer, another 2 in one layer. So you have here total of 4. This is good. When you come to the rebars here, at this point, while you're going to the right, or this point, you're going to the left, we're going to say here, I provided 2 rebars. You cut just the section here, right? You cut the section here, count number of rebars. So here I have 2, and here I have 4. The first 2 rebars that's going from the beginning to the end, this is simple. I can just say, let's put it from the beginning to the end. The problem is going to be at this 2 rebars. Where do you stop them? Is it okay to stop them right here? Because this is where the moment says that I don't need it. So I'm going to say, it means if you're going to be moving here like half an inch, you can say, okay, let me go here half an inch. I'm going to have some moment. I'm going to have here some tension force. This tension force that I still have in the beam needs to be transferred from this rebar to the concrete. And you don't have enough distance, it's only 1 inch. So we can say now, let me extend the rebar a little bit so that I give enough distance to transfer the force from the rebar to the concrete. This distance, this length, beyond the point that I don't need the rebar at, is called development length. So let me take you here back to the first slide. This is the meaning of this development length. This can be the length that you need to develop the bar through. What does it mean by develop the bar? It means to completely take the force out of the rebar to the concrete. I guess at the beginning, I explained the meaning of a splice. I said the splice meaning to put the rebars next to each other. Development means to extend the bar for a certain length to be able to take the force out of the rebar to the concrete. How about splice? Splice length can be this length needed to take the force out of the rebar to the surrounding concrete and then back from the surrounding concrete to the next rebar, which is the adjacent rebar. This is the one that you're trying to splice the rebar with. Any questions? Yes? All right, let's continue. Just imagine how the rebar is going to work. Let's say here's you have 4 rebars and look what happened. They come like this and then they go up with a hook. And these 3 bars, they come like this and then goes down with a hook. Now, just imagine that you have a hook at the end of the rebar versus no hooks. You say, okay, here is 1 rebar, just a straight piece. You say it like this versus another rebar with a hook. Would like to see an example? I can go back to this slide. Here is 1 rebar that goes straight, no hook. This rebar here goes with the hook at the end. Like in here, this rebar is straight, just ends like this. This rebar ends with the hook. So I'm going to be taking here 2 rebars. One is going to be with the hook, one without the hook. You guys following me? Because I'm going to be asking questions. Is everybody here? Yes?
Yes.
Yes.
Okay,
Yep.
great. So in each one of them, I'm going to put the same tension force. Tension force in the rebar. Same amount of force. I put here, I'm going to say this is going to be just T. Let's give it the same tension force, same value. Now I need to develop this rebar in the concrete, both of these 2 rebars. Do you think that both of them will need the same length to take the force out to the concrete? Or one of them is going to be shorter than the other? I'd like to hear from you. Can someone answer, or should I pick people?
Can you ask that question?
All right. As everybody's listening here, what I'm saying is I'm going to be asking questions, so please stay focused with me. I have here 2 rebars similar to each other. The difference is one ends with a hook, the other one is just a straight. I have the same tension force applied on each one of this rebar. I'm going to be taking this rebar and develop it into the concrete. Anyone has a question of the meaning of development before I continue my question? So everybody understand the meaning of development?
No, can you explain what development means?
Sure. Now I need to start all over again from the beginning. All right. When it comes here to this beam sample that I'm looking at with this reinforcement, based on the moment diagram, I need here 4 rebars, and here I need only 2 rebars. A good way to detail it is to keep 2 rebars continuous from the beginning to the end. How about the other 2 rebars? Because here I need 4. I'm going to say I'm going to put 2 short ones here. So when you cut a section here, I provided 2 and 2. I provide here 4, whatever is needed. And when you take a section here, you're going to say, well, you just need here 2 rebars. Now I cannot just stop the rebar here. I need to extend it a little bit, right? This rebar, right? I need to extend it a little bit from this side to be able to take the additional force that I have in this 2 rebars to the concrete. This process, or this meaning, we call it here development. So what does it mean by development again? Development means taking the force in the rebar and transfer it completely to the surrounding concrete. This is the meaning of development. Now back to my question. I have here 2 rebars. One is a straight, the other one was a hook. Same tension force applied. Now I need to develop both of these 2 rebars to the surrounding concrete. Which one do you think is going to be taking a longer distance to develop the bar? Or which length do you think is going to be higher to develop each one of these 2 rebars?
I'm sorry, Professor. You said development means to take the force in the rebar and then do what?
Transfer it to the surrounding concrete.
Okay, thank you.
Are we clear now on definition of development of a rebar? Anyone here doesn't understand the meaning or not clear to him? All right, so I need your help here. Which one do you think, which development length is going to be longer? Is it for the straight rebar or the hooked rebar?
I believe it's going to be the hook
The
rebar.
hooked? Hooked will need more length? Or the straight would need more length?
If you phrase it like that, then the top one would need more length.
The top one will need more length, or the bottom one would need more length to take the force out of it to the concrete. In other words, do you think that this hook here is going to impact transfer of the force from the rebar to the concrete?
Yes.
It's going to be providing more, I'm going to say here, more transfer of the force, transfer mechanism of the force from the rebar to the concrete? Yes or no?
Yes.
So in this case, this rebar length is going to be shorter. Why? Because transfer mechanism is going to be happening by bond between the rebar and the concrete, and also by the hook. So let's say if the hook is taking here 50% the force transfer to the concrete, the rest 50% will be needed in this length. While the 100% of transfer of the force is going to be happening here throughout the straight length. Now, this means that straight development length is going to be longer than hooked development length. This makes sense here? Why? Because the hook itself is going to help out. Here, you don't have any hooks. So it's going to be all based on the bond between the concrete and the rebar. Here, you have the bond, yeah, throughout this length, shorter length, but you have also the help of the hook, because this hook is going to be bearing in concrete. Just if you like to imagine here the size of a hook, let's say for number 18. Just, you know, a person is going to fit here. This is about 6.5 feet. And you see how big the hook, just for you to understand the magnitude of the hook for big rebars. Here is transfer of the force. How the force is transferred from the rebar to the concrete. Here's a piece of the rebar. Here's the amount of tension and force that you have on it. And these little arrows, they represent the bond between the concrete and between the rebar. So whenever that you have tension force here at this location, you need this length to be able to take the force from the rebar to the surrounding concrete. If you take this bond stress multiplied by the area of the surface, right? The surface area of the rebar. And how much is the surface area is going to be equal to? You're going to say when it comes to here, it's going to be pi times d. Pi times d is going to give you the perimeter of this circle, or perimeter of the rebar, times the length L. So I simply can say here, the force, the tension is going to be T equal to the tension the rebar. Right? The bond force, which is the force transfer from the rebar to the concrete, should be equal to it. So I'm going to say bond force, I'm going to call it B. This is going to be the bond force. It has to be equal to the tension force T. They need to be equal to each other. Otherwise, you are not really developing the rebar. So in order for you to develop it, B will need to be equal to T. So what is the force B? The force B is going to be the force, the bond force between the rebar to the concrete. It's going to be equal to the following. The surface area. How much is the surface area? I'm going to say it's going to be equal to pi times diameter of the rebar times D. So this is going to be D times pi is going to give you the circle perimeter times L, the length of the rebar. This is going to be L, lowercase or uppercase, right? Now this is going to be the surface area times the bond stress. You can see here bond stress. And these two forces needs to be equal to each other. Otherwise, you're not really developing the bar. This bond stress is going to be based on what? I need to figure out what is controlling this, because bar diameter is going to be D, right? I need to maximize these values as much as I can. Pi is a constant, I cannot change it. D is going to be the diameter of the bar. I mean, let's say that I have number 6 rebar. So I'm going to say it's going to be 3/4 of an inch. So it's gonna be based on the rebar size. L is the number I can play with. This gonna be actually our test is to figure out this development length. How much is this L? Am I gonna be going here with 2 feet, 3 feet, 6 inches? This is what I need to be able to design my details when it comes to reinforcing. Multiply by bond stress. So I'm gonna say bond stress is a big deal. What is this based on? It's gonna be the question, right? What is controlling this bond stress? What bond? I'm gonna say the bond between the concrete to the rebar. I'd like to hear from you. Can you help me, Brian, with this? In your opinion, what's controlling the bond stress between the rebar and between the concrete?
Yeah, can you guide me through it?
You have here the rebar embedded into the concrete, right?
Uh-huh.
If you want to pull this rebar out, what's resisting? I'm gonna say the bond stress between the rebar and between the concrete.
Okay.
My question is, in your opinion, what is impacting and affecting the bond stress? What's controlling it?
What's controlling bond stress?
Yeah, like what are the factors do you think that I need to study to
Shear?
be able to come up? What shear?
Like when you're because you're saying you're trying to pull it out now, so I'm assuming there's
Yeah,
like
I'm
a
just trying to pull it
shear.
out. There is no shear. Yeah,
There's no shear.
this bond stress is like shear stress. This is correct. Yeah, it's kind of shear, right? But I mean, if you increase the concrete strength, would that increase the bond stress?
I would assume so, yeah.
Okay, good.
It'll
So
make it harder to
I'm
pull
gonna
out
say
now.
factors. Yeah, I'm gonna say factors. This is gonna be F prime C. This is gonna be the first factor. This is gonna be one item, right? What else beside the concrete strength?
Me again or someone else?
It's someone else, Adrian.
Okay.
Yeah, so length and diameter would be a factor as well.
Factor to control the bond stress. Would that impact the bond stress or impact the full force B?
The force B.
The force B. This is true. It's gonna be this and that. This is correct. But how about the bond stress? I'm trying here to study the bond stress only. So can you help me here with the bond stress? What is impacting the bond stress? We can say F prime C. What else?
Is there some type of friction in there that's impacting the bond stress, maybe?
Like what?
Hmm.
For example,
rib on the,
let me give you a hint. Do you think that this distance is important? The edge of the concrete? Because when you look here at the concrete section and then you put a rebar here, right? Do you think that this rebar, the bond for this rebar is going to be the same as the bond for this rebar? You think that the bond for both rebars is going to be the same here? Which one do you think would have more concrete surrounding the bar itself? Is it here or there? At the
Middle.
bottom or the top?
The top.
The top has more concrete, right? We're gonna say the edge distance. If you put the rebar right here, right, you don't have enough concrete to surround it. Maybe you'd like to push it a little bit this way, right? So you say the amount of concrete surrounding the rebar is gonna be very critical. Another factor. You think if I put here 2 rebars or 3 bars next to each other, like the rebar spacing is an issue? If I put 3 rebar versus just 1 rebar, which one do you think that you're gonna have bond stress, bigger bond stress with? When you have 1 rebars versus 3 rebars?
I think one.
Yeah, 1. Why? It's simple. Because this rebar, it has all of this concrete to help out. Look at this. All of this concrete, this volume of concrete is helping it, right? But once I'm going to start here to put another rebar next to it, right? Another rebar next to it. This gave a problem. Why? Because there is no enough concrete surrounding this rebar by itself. You're gonna have other rebars sharing the same concrete. All right. How about, I'm not sure if you guys hear about this epoxy coated rebars. Did you guys hear about it before? When you coat rebars with epoxy? Did you hear about it?
That's to
No.
make them more like weather resistant, right? Like rust
Yeah,
proof.
yeah. To increase the resistance for corrosion. What do you think this epoxy coating is going to be doing? Would that increase the bond or reduce the bond?
Say it decreases.
It decreases, right? Because you put like a coat on the top of it, as if you paint a surface. Just imagine you have some steel, right? You paint the surface. You paint the steel with paint, any paint, it doesn't matter what paint, right? You're going to make it more slippery. It means that you're going to be reducing the bond between the rebar and the surrounding concrete. So we need to study all of these factors to come up with our length. I'm going to say what length? I'm going to say development length. I'll give you the big question. How can we come up with an equation to figure out this development length? Here's the bond. If you'd like to put the rebar this way, I'm going to say we call this deformation. So you can call it knots if you want to, but actually, or reps, but actually it's called deformation. It's going to be the bar deformation. If you have a smooth bar versus a bar with some deformation, would that impact also the bond? So it's going to be a rebar like this versus smooth bar. Which one do you think would have higher bond? Let's say, of course, the one with deformation. This is why all the rebars, they have this deformation. I'm sure that you guys have seen some rebars, right? The reason that we have this deformation is to provide some bond between the steel and between the concrete. So, okay. Here's the edge distance. What would happen if you have two rebars like this? Potential crack is going to happen like this, or mode of failure. If you bring this rebar close to the edge, this is going to be the edge distance. And the amount of surrounding concrete is going to be much smaller. How about here? Same. How about here when you bring it down? It's going to be the potential crack. So you need to have enough concrete cover. And this is also one of the items that you need to have a cover and the spacing between the rebars. If you bring the rebars close to each other, it may crack in this fashion. Yes? Questions?
No, sorry about that.
Sorry. So the spacing between the rebars is going to be critical. You try to set them further away from each other so that each one's going to have enough concrete. But here, when you set them close to the edge, the crack may happen here. So actually, some of the distances and dimension that I need to study is going to be maybe this edge distance and this edge distance, right? It's going to be critical to me. And the spacing. Spacing is going to be important. When I have bigger spacing, I'm going to have more bond, shorter length. If I have big cover, I'm going to have more bond. There's another thing here, which is location of the rebar. If you put the rebar here in the bottom or the top of the beam, which one do you think is going to be needing longer distance? You can say here is a beam section. It's going to be the entire beam section. Comparing here between two rebars. One of them is going to be right here at the bottom. And one of them is going to be here on the top. Which one do you think is going to have higher bond, provided that edge distance is going to be the same? Top or the bottom? Yes? Daniel? Daniel or Greg?
Would
Yes?
the bottom have more?
The bottom is going to be more bond?
Yes.
Yes. Why, Caesar? Why do you think so? Can you
Because
explain?
the concrete's sitting on top of it, so
Exactly. Yeah.
Yeah.
So here you have more pressure from the concrete. Here you are going to have less pressure. That's correct. When you have more pressure, it means that you provide here more bond. Very good. So this is what I was talking about in detailing of steel. Let's say here's the top rebars. And I need here, how many rebars you see? 5 rebars, right? The top, here's the section. When you look here at the elevation, see that I'm gonna have here something that I call here X bars, and some that I'm gonna be calling here Y bars. X bars is gonna be continuous. Y bars, I'd like to make it short. I don't really need them here. So I need to develop this rebar. L sub D means development length. In plan view, I need to pick which is gonna be the X rebars, which one's gonna be the Y rebars. You see here, they happen all in the same layer, same elevation. They're all in the same location, right? But in here, just for the illustration, we show that this rebar is dropped down. Otherwise, if I stop the rebar here, you're not gonna see it. It's just the way to show it. But in reality, they are all in one layer. In plan view, which means when you look here from the top, you look like this, right? You look at this beam from the top. You're gonna say this is gonna be my X bars and this is gonna be my Y bars. Therefore, this is gonna be a Y bar and this is gonna be also be a Y bar that I need to stop at certain location. Just an example for how you detail the steel. The ECI here gives me an equation. Figure out this L sub D development length. It looks complex because it has weird parameters, right? We call this psi. This symbol here is called psi. Let me go through the equation quick first. Try to understand what symbols are we talking about, what parameters. The first one, 3 divided by 40, this is a constant. So I don't have to worry about this, right? It's nothing, just a constant. F sub y, yield strength. Yeah, I know yield strength. F prime C, concrete strength. Lambda is gonna be this factor for lightweight concrete. We know lambda, we went through it before. So I say here, this section or this term of the equation is simple. Just like concrete parameters that we know of and constant. From the right side, I'm gonna say this is here, the bar diameter. You are trying here to develop number 8 rebar, it's gonna be 1 inch. You're trying to do number 4 rebar, it's gonna be half an inch. So it's gonna be the bar diameter that you're trying here to develop with splines. So I guess the tough part is gonna be this one that we're trying to understand, right? The middle one. Am I correct? And this is the stuff that I haven't seen before, new factors. Factor says psi sub t is a factor because something say here t. T is gonna be what? Top. You say C stands for top. Multiply by psi sub e. What is E? E stands for epoxy. Coating. Psi sub s, I'm gonna say this is gonna be for the size of the rebar size itself. I'm gonna see this factor. Are we good? So again, constant, F sub y yield trends, F prime C concrete, of course, is gonna be in PSI. And this number here, when you put it, you need to put it in PSI, which means 60 is gonna be here 60,000, right? What happens if you just put 60? You get very short length for the development. I'd like to continue, I'm gonna say, what is CB? CB, I'm gonna say the clear distance. I'm gonna say some clear distance. We'll figure this out, we'll work on it. TTR, they say, well, it has some value because if you have some reinforcing bars like ties, this is gonna be accounting for it. Code says you can just use it as 0. I'm gonna say, you know what? 0. Let me just ignore it. This is gonna be a simple analysis. How about DB? I'm gonna say the bar diameter. Again. Now I simplified the equation a little bit. Let me see here the impact of each one of these factors on the development length. When you have higher yield point or high yield trends, let's say grade 40 versus 60 versus 75. Do you think that grade 60 or 75 would need more length than grade 40 in the development length? Answer is yes. You increase F sub Y, L sub D is going to increase, which means here that you're going to have bigger force to transfer. You remember the force that we're trying to transfer? T AS times Fy. This tension force is going to be based on F sub Y. So it's true, it makes sense. When you increase the concrete strength, what's going to happen to development length? I'm going to say development length is going to be shorter. Why? Because concrete is going to be providing more bond. So if any factor here is going to be at the denominator, it's going to be increasing the bond. Any factor here on the top is going to be increasing the length, which means increasing the tension force that you have there, or reducing the bond. Epoxy coating, when you put epoxy, this factor is going to be more than one. What's this going to do? It's going to increase the length, which means reducing the bond. Same thing for the bar size. Same thing for the top. You remember when I asked this question about top bar versus bottom bars? We say in top bars, I need more length. In bottom bars, I'm going to have concrete pressure on top of it. So this factor here is going to be more than one for top rebars. All right, I'd like to see this factor. So this is the whole thing. Just use the equation. Understand these terms and use them correctly in your equation. I have another condition here. It says this CB plus KTR, which means this section or this term, they say it has to be less than or equal to 2.5. So I'm going to say, how about if I try the number and find it to be 3, what should I do? You say, just use 2.5. So 2.5 is going to be like the cap. You're limiting this factor to 2.5. So, okay, good. Let's see here definition of this C sub B. What's the definition of the clear distance? I'm going to be taking here an example. Here is one beam section. You have here couple of number 8 and number 4 ties. The distance here, this clear, is 2 inches to the tie, and this clear, you see, look at this, from the side is going to be the same. So it says here typical, which means the top is going to be the same as the side. Now, CB1, definition of CB, according to this equation, it's not this clear to the tie. It's going to be from the center of the rebar to the edge of the concrete. So in this code here, they say, well, this C sub B, it means distance from edge of the concrete to the center of the rebar. How about this CB1? This CB1 equals 2 inches plus tie is going to be number 4, is going to be half an inch, plus half an inch to the center is going to be total of 3 inches. The C sub B is going to be 3 inches. Here's the analysis for the calculation. 2 inch for the clear cover to the tie, half inch for the tie size, additional half inch for half of the rebar size. Any questions about CB1? Can I ask? Jose? Jose?
Yes, Professor.
Yes. Do you have any questions on CB1?
Can you just kind of go over it again once more?
Okay. Trying to figure out here, excuse me, I'm trying to figure out CB1. What is CB1? It's distance to the center of the rebar. This is to confirm this discussion here on when you bring the bar closer to the edge. This distance from the center of the bar to the edge is going to be called CB. According to this equation, it's going to be this CB. I need to figure out how can I do this CB. In this example, I have 2 inch clear plus half inch for the tie size plus half inch for half of the diameter, like the radius of this rebar. Total is going to be 3 inches. I'm going to call this here CB1. Yes, Jose. Are you still there?
Yes, Professor, that makes sense.
Okay, so my question is, what is this, the first half an inch? What is that for? Do you see the hand? Yes, Jose?
Yeah, I see it. Give me a second.
So, yeah, okay. Elias, can you help me with that? What is this half inch for?
So the first one could be the thigh size,
Yes,
And-
thank you.
and the second one could be the half of the bar size, basically.
Very good. Thank you. Thank you, Elias.
Of course.
Okay. Now I have another CB to account for the spacing between the rebars, right? Because we said, well, here's another problem. If you bring them close to each other, I'm gonna have some trouble here for the spacing. If you bring it close to the edge, I'm gonna have trouble here with the amount of concrete around it. I'm gonna say second issue when it comes to CB is gonna be the spacing. So the second CB I need to calculate out, it's not gonna be really the spacing, it's gonna be from the center of the rebar to some imaginary line like this dashed line between the two rebars. So the spacing here, it says 3-inch clear from face of the rebar to face of the rebar. You can say, how about CB2? Say, okay, how much is the distance, total distance from center of the rebar to center of the rebar? If this here 3 inches, I can add half an inch from this side, half an inch from this side, it's gonna be 4 inches. Divide by 2 is gonna be 2 inches. Here we go. It's gonna be half of the 3-inch clear plus 2 half of each bar diameter from each side. It's gonna be a total of 2 inches. I guess when CB is gonna be small, I need to go with the smaller value. Why? Because the smaller value is gonna be more critical. You see this CB? When this becomes smaller, what happens to the length? Length is grown up. So I have here 2 values for C sub B. In the analysis, I have one of them at 3 inches, the other one's gonna be like 2 inches. Which one should I pick? I'm gonna say, let me go with the smaller. It's gonna be more critical. It's gonna be controlling my design. Just an idea about the CB, how can I do it? And actually, this is taken from an example that I'm gonna be going through today. And with that, we at least we cover this CB discussion. We know how to do it. Now, as we said, we have 3 factors: psi sub T, psi sub E, psi sub S. The first one is gonna be for the top. It says this factor is simple. If psi on the top here is gonna be 1.3 when you have top rebars. And for bottom rebars in vertical, that's why it says here other reinforcement. What does it mean by other reinforcement? You can say bottom and verticals. What happened there in the 3 bars? Psi sub T is gonna be equal to 1. So what constitutes the top rebars? It says when you have more than 12 inches of concrete below it. Yes, okay. Here's one of the beams. I have an example like this. Rebar on the top. Here's a rebar, right? The whole thickness of the slab or this section, I'm gonna say this is only 8 inches. And this rebar is giving the top. Is this treated as top rebar in this equation or treated as to be bottom rebars? Daniel? Daniel is not here today. Juliana?
Yeah.
Yeah. So the whole slab thickness is 8 inches. Just like in a slab, in a concrete section. I have here a rebar that it looks to me to be in the top. For this equation here, should I treat it to be top bars or bottom bars?
Would you treat it as a product since it's less than the 12 inches?
Yeah, I mean, do you think that in here, do I have less than 12 inches of concrete or more?
Is that 8 feet or 8 inches?
8, yeah, 8 inches. Just the whole section here is 8 inches. You see here that I have more than 12 inches below the bar? You're gonna say no, because the whole thing is 8 inches, right?
Mm-hmm.
And this could be maybe an inch clear, so maybe 1.5 inch, this is gonna be 6.5. So would I consider this to be top bar or bottom bar? For the
Bottom bar.
analysis, it's gonna be bottom. This is correct, thank you. Why? Because it just says simply what defines a top bar in this equation when you have more than 12 inches of concrete. If you have less than 12 inches, you consider to be bottom bars or other reinforcement. So, okay, good, nice, simple, check. Item number 2, psi sub E. This gave you for the coating factor for the epoxy. It says it could be 1.5, 1.2, or 1. Depends on what? Depends on the cover and depends on the clear spacing. If no epoxy coating, it's gonna be just 1.0. It can be 1.5 when you have very small cover. When the cover is less than 3 times the bar diameter. Like an example, cover is 2 inches. The rebar is number 8. Is psi sub B is gonna be 1.5 or 1.2? Someone's gonna say, okay, can we write it down? I'm gonna say, yeah. Cover equals 3 inches. Rebar equals, let's say, you take it back 2 inches. Rebar number 8. What is your psi sub E? Is it 1.5 or 1.2?
1.5.
The cover is 2 inches, less than 3 times this. You say, okay, yeah. So I'm gonna be belong to here, right? I belong here. So it's gonna be 1.5. To be able to use here 1.2, you need to increase the cover or reduce the bar size. If this had been here 3 inches, I'm gonna say, yeah, 3 inches. So the cover here is more than or equal to 3 times the bar diameter, right? So I'm good. I'm gonna go there 1.2 if I do epoxy coating, right? It says here, once you're done with this psi sub T, psi sub B, just multiply by each other. D cannot be more than 1.7. So let's say analysis showed to be 2. What would you do? You're gonna say, just use 1.7. It could be like the cap, the max value that you can use. I have a third factor called here psi sub S. I'm gonna go back here to the original equation so that you guys know where are we at. We're done with this section. We did the psi sub T, psi sub E, we did the C sub B, now we're doing psi sub S. Let's see, psi sub S is gonna be based on the bar size. It's a factor, additional factor. When you have a smaller bars, number 6 and smaller, you take it 0.8, which means more bond. When you have number 7 and larger, it's gonna be 1.0. Okay, yeah, I understand. About the lambda factor, the 0.75 for lightweight concrete. We have gone through this already in the past. How about definition of C sub B? I'm gonna say, yeah, this gave you like the spacing or the edge distance. We went through this already now. KTR, I'm gonna say, you know what? Just take it equal to 0. Forget about this equation. Don't need it. This is good. I'm gonna put here a little box around it. ACI also give you like a table. This table is a very simple table. For this case of D, which means this 4 factors, you can just have from the table. I'm gonna say, what are these 4 factors? Say, let me go back. You see this term, 3 divided by 40, F sub Y, lambda, F prime C. It's just additional table to simplify the analysis for this. For me, I wouldn't do it this way. Just gonna do the analysis. I don't really need this table. I'm gonna say, forget this table. It doesn't help that much. I can just do a couple of numbers, right? Just do the analysis myself. All right. Now, summary, I'd like to see your steps. How can I solve a problem like this when I see it in my homework or project or the exam? This is not coming in your second midterm. That's giving in the final. Number one, do case of D, either from the table or the equation. What's case of D? I'm going to say this term here, this factor. In other words, it's going to be this factor. Just do this first. So, okay. Number two, find out size of T, top, epoxy, size, and the lambda factor if you have lightweight versus no lightweight. All right, so you did size of T, size of B, multiplied by each other. This gave me more than 1.7, just use 1.7. Item number 3 or number 4. Find out C sub B. You can say, where do you do here C sub B? I'm going to take you back. This is going to be the C sub B analysis, right? Spacing and edge distance to the center of the rebar. After this, you do KTR. KTR will say, just set it here equal to 0. Now do this factor. If it's going to be more than 2.5, just use 2.5. This KER is kind of a reduction factor that maybe later we can discuss it. After this, you do L sub D. Your minimum L sub D is going to be 12 inches. So you cannot go lower than 12 inches. You can go to 16, you can go to 18 inch, 20 inch. If you do the analysis, you have, let's say, 10 inches, just use 12. It's going to be the minimum, all right? So, okay, an example. Ready for the example? Yes or no?
Yes, sir.
All right. You're going to take a couple of minute break before we continue. So here's our example. You see here a section of the beam. It seems to be top rebar. And the reason I know it, because you see this, from the bottom of this rebar to the concrete, it shows here more than 12 inches. So I'm going to treat it as top rebar. By just looking at this, you can see here, I have seen this for CB analysis. You remember the C sub B? I'm going to go back here a few slides. Say, let me see here the C sub B analysis. Said, yeah, that was exactly the same. That was taken from this exercise, from this example. I have here 2 inch clear, typical, which means top and to the side. I have clear spacing of 3 inches, and here's the analysis for CB1 and CB2. Now I'm going to move forward here to my example. And say, yeah, it's going to be the same deal. It says here, calculate the tensile development length required for number 8 top rebars. So the size here is number 8, yes. More than 12 inches of fresh concrete to be cast below the rebar or below the bars. You see, okay, yeah, more than 12 inches. This is going to be top rebars. Meaning if size of T is going to be equal to how much? We're going to go back here. What's the size of T values? 1.3, not 1. Okay, good. It says here lightweight concrete beam, which means I need to use here what factor for lightweight? I'm going to say 0.75. Yield strength 60,000 psi, concrete strength 4,000 psi. The stirrups is number 4. All rebars are uncoated, which means if psi sub E for the epoxy is going to be equal to 1.0. There's no factor for that. So, okay, good. First, the K sub D factor. What's K sub D? You can say, you know what? Let me move here. K sub D is going to be this factor here. I'm going to go back here a few slides, just show the main equation that we started with. I'm going to say, here is equation. What's K sub D? It's K sub D, which means this constant, and F sub Y F prime C. You can use a table if you like to. You go to F sub Y of 60, 4,000 concrete is going to be 71.2. This K sub D is here 71.2. But you can just use your calculator if you want to. It's okay. 71.2. Now I have top rebars, it's confirmed. So I'm gonna say 1.3 for top rebars. No epoxy, so psi sub E is gonna be 1.0. Uncoated bars, right? It says here number 8 rebars for number 7 and larger is gonna be 1.0. So number 8 is gonna be 1.0 for the size. I have lightweight concrete, lambda equals 2.75. Now let's do here this product of 1.3 times 1 is gonna be 1.3. This product, if it goes above 1.7, you just use 1.7. It is already 1.3, I'm gonna keep it as 1.3. C sub B analysis, I'm gonna say we did this already, and then we say 2-inch controls by design. So C sub B is gonna be 2 inches. Code says you can ignore the effect of the tie in the bond, meaning take KTR equals 0. So this factor here, C sub B plus KTR divided by DB, I did the analysis, turned to be 2. If you have here 2.0, you do a check. You compare it with 2.5. If it is higher than 2.5, you keep it as 2.5. If it is lower than 2.5, you take the value as is. So it's gonna be 2.0. I'm done almost with all the steps. So my next is to use the equation. Here's my equation. I'm gonna put here K sub D, I'm gonna put the lambda factor, put the psi sub T, 1.3, no epoxy is gonna be 1.0, number 8, which means number 7 and larger is gonna be 1.0, this CB plus KTR divided by DB is gonna be 2.0, bar diameter is 1.0, it's gonna be 1 inch. I run the analysis, run the equation, I'm getting here 61.7 inches. I need to check it here against 12 inches minimum. I cannot ask for 61.7 inches in the construction side. So I'm gonna call it here 62 inches. It's gonna be my development length needed. Any questions? Do you have here any questions? I'm sorry.
Why does it have to be greater than 12 inches, the development length?
Why it has to be? Good question. Thank you for asking this. I'm gonna take you back here to one slide. You know that this equations here is coming from the ACI, like the code. The code says your minimum is gonna be 12 inches. And why would the code do that? Because less than 12 inches is gonna be almost nothing. So they need to put a minimum value for it.
Makes sense.
Makes sense? It's like a code value. But you know, in many cases, certain code values, you're gonna say, why didn't they say 10 inches? Right? Why didn't they say 6 inches? You can say someone has done some testing and they find out that if it's gonna be less than 12 inches, performance is gonna be very poor. They said, well, let's go here, stick to a number, 12 inches is good, like a foot. They just use it and put in our code. This is only reason.
Thank you.
No problem. All right.
This length is only good for the straight bar or the hook too?
Hook is gonna have different equation.
Okay.
Very good question. Thank you. Good question. Who asked this question? Adrian? Isaias? Okay, good, Isaias.
Yeah.
Good. All right. Very good. Next time I'm gonna go through this, the hook. But I have another example here. It says calculate development length required for number 9. I guess once I start to read it, some factors are gonna be triggered. The psi sub s for the bar size is gonna be 1.0. In the top of a 15-inch thick reinforced concrete slab, You say here's 15 inch. To qualify this to be top rebar, I need to have 12 inches of concrete below it. I have here 3/4 of an inch. Number 9 is 1 1/8 of an inch. You say, let's say 1 1/4, right? It's gonna be 2 inches. Yeah, so I have enough concrete. So it's gonna be top rebars. F sub y is gonna be 60. F prime C is gonna be 4 KSI. If no one said normal weight concrete or lightweight, I'm gonna be assuming it to be normal weight, just you know. If they say there is some epoxy, I know. If nothing was mentioned, it's gonna be no epoxy. In this case, it says here epoxy coated. So I need to look at the spacing. Look, this can be sectioned through the concrete. I need to look at the spacing. Spacing and cover is gonna be important for the epoxy factor. If you remember, we have 3 factors for the epoxy. 1.5, 1.3. Is it 1.3? Let me go through them again. I have its 3 factors: 1.5, 1.2, and 1.0. So I need to know, since they say it's gonna be epoxy coated, which one's gonna be the 1.5 or 1.2. Move forward. K sub D is gonna be 71.2. From where? The table for the constant. If psi sub T, now we have top rebars is gonna be 1.3. The bars epoxy coated, so I can have 1.5 or 1.2. I need to do the check. You compare here the cover, which is 3/4 of an inch, with 3 times the bar diameter. Which one's larger? This is gonna be here 1 1/8 of an inch. Even if you assume this to be number 8, you have number 8, 1 inch, and the cover is gonna be only 3/4 of an inch, much less than what? Much less than 3 times the bar diameter. So if psi sub E for the epoxy is gonna be now 1.5. Okay. Psi sub S, number 9, which means number 7 and larger, is gonna be 1.0, right? So it's gonna be 1.0. Normal weight concrete, lambda is gonna be 1.0. I'm gonna try here and do 1.3 times 1.5. Psi sub T times psi sub E. Try this product, it's gonna be 1.95. I'm going above 1.7. So I'm gonna keep it as 1.7 in my analysis. Let me go here back one, let me move forward one slide. I'm gonna go back in a second. Look at the equation here. Psi sub T, psi sub E. I just put 1.7. I didn't put 1.95. C sub B, 1 and 2. Usually 1 is gonna be about the clear, and 2 is gonna be about the border spacing. So let me go to it and figure out CB1 and CB2. CB1 is gonna be the distance from the center of the bar to the concrete, surface of the concrete, meaning from here to here. This point. I have here 3/4 of an inch cover, as it says here, 3/4 of an inch, plus 1 1/8 of an inch divided by 2, 1/2 of the bar diameter. Here C sub B, 3/4 of an inch for the cover, plus 1 1/8 divided by 2. Number 9, because each bar size, let's say number 8, number 7 is gonna be 7/8. So I have here 1.3. When it comes to the spacing, look at this. Come to the spacing, center to center, it says here at 8 inch. So come here, you do the imaginary line between them. It's gonna be at 4 inches from the center of the rebar. So from here to there is gonna be exactly 4 inches. Now you compare 4 inches, which is CB2, you compare it to 1.3. Now it's gonna be controlling. So this is gonna be the value I need to use in my analysis. Here's my equation finally. KD and lambda 71.2 divided by 1.0. If psi sub t, if psi sub b is gonna be 1.7, if psi sub s for the size is gonna be 1, d sub b is gonna be 1 1/8 of an inch. Now I need to look at this factor here that includes KTR, which is 0. I'm gonna try this term, and this term I have a limit of 2.5. I tried this term, it turned to be 1.165, less than 2.5. I'm gonna be using as is. Times again the bar diameter. I'm getting here 11 or 117.2 inches. There's no comparison here, it's 12 inches. It is shown here to be 118 inches. In reality, I just use here 120 because you're talking about 10 feet, right? It's just easier when you say 10 feet. 2 inches not gonna change the world, right? In terms of the cost. Any questions? We're done with this slide set. I'd like to see here if you guys have any questions.
Sorry, you said if it didn't mention if it was normal or lightweight, we assume lightweight, or
Yes,
do
you're
we
normal.
assume?
By default is
Okay.
normal. And by
Okay.
default, no coating. But in this problem, they said, this is example, right?
Yeah.
And this example here, the second example, right, says normal weight concrete. In the first one, it says lightweight concrete. But in general, if nothing is mentioned, it's gonna be normal weight. If nothing is mentioned, no epoxy coating.
Okay. Thank you.
Thank you for the question.
We're solving, when you were solving CB1, what were the two values that you did half of the tie and half of the rebar?
In general, the CB, meaning it's gonna be the distance from edge of the concrete
Uh-huh,
to the center of the rebar. Okay,
okay,
so this is the bar that I'm trying to work with. This is the one, right? This guy here.
yeah,
So for each rebar, you have the spacing, because you can you consider this to be a measuring line. So this is gonna be 1 from free edge to the center of the rebar. And it's gonna be this one from this free edge to the center of the rebar.
yeah,
So where is this free edge? I'm gonna say 2 inches plus half an inch plus half an inch is gonna be 3. About here, you say I'm gonna put this imaginary line right in the middle between the two rebars. This here 3 inches, so it's gonna be 1.5. 1.5 from where to where? You say 1.5 from this imaginary line to the face of the rebar. You take here 1.5, additional half an inch, center of the rebar, it's gonna be here 2 inches. Where's the analysis for it? It's gonna be right here.
so how did you know that the stirrup was half an inch? Is it because of the number, the size?
Because the rebar size. This rebar,
Okay.
oh, the stirrup, this is stirrup.
Yeah, the stirrup, yeah,
Is here number 4. Look at this. You see it?
yeah,
You my
okay,
screen, right?
yeah.
Number 4 means half an inch. It's gonna be 4/8 of an inch.
Oh, okay, that makes sense now.
Okay, right. Yeah, more questions. You're good? Next slide set. Same topic. But now we're going to be doing the hook. This is the question been answered, right? Size? So here's the hook. I need to look for an equation for the hook. I have 3 types of hooks. We call this 9-degree center hook. Why standard? Because this length here would come as 12 dB. For 180 degrees center hook, or 135 cross ties. Question is, what is this L sub D for the hook? I'm gonna put this slide back again. I'm gonna say, what does it mean by L sub D in general? L sub D is gonna be this length at which you transfer the force from the rebar to the concrete. Like in here, this is gonna be L sub D. We just call it here L sub D, development length. For the hook, we call it L sub DH. You see this? LDH, development length for the hook. Of course, it's gonna be much shorter. Much shorter. Like here's LDH, right? Let me see here the equation. Look at the equation, much simpler. Look at this equation here. It kind of looks like it, right? Some factors, you have F sub Y, here you have also square root of F prime C. You have lambda factor, you have D sub B, you have only 0.02 and psi sub B. Other factors do not count. This is good, much simpler. And psi sub B is also much simpler. It says sub B is equal 1.2 or 1.0. If you have epoxy coating, it's gonna be 1.2. Nothing is gonna be 1.0. For this one here, for a straight development, I have 3 values. Here, just 2 values. 1.5, 1.2, 1.0. Here, just 2 values. 1.2 or nothing, 1.0. Lambda is the same. And it says here, LDH shall not be less than one of the following, the smaller of the two. 8 times the bar diameter or 6 inches. Where is this coming from? You can say the code. ACI says so. This is gonna be a code value. Now, I have here some factors that controls here my design, my analysis. I'm just gonna be skipping here. We can go back to them. But in general, they say we have some modification factors, multipliers. This multiplier here is going to reduce the length of the hook of LDH. Why? Because it's going to be less than 1. It says here 0.7, right? Here's LDH, hook length, and it's going to be multiplier times LDH. Could be 0.7, could be 0.8, could be 0.8. So all of these factors could help to reduce the development length for the hook. It says here, when the side cover is smaller than 2.5 inch and you have 9-degree hook, and additional condition, you can use here 0.7. Okay. It could be also 0.8 for 9-degree standard hooks, whose number is even smaller. And if you have some ties around it, or you have stirrups perpendicular to the rebar being developed and the spacing is small, right? The spacing is not smaller than, which means larger than 3 dB. What's going to happen? We can reduce it to 0.8. Same thing also for the 180-degree hook, another reduction factor if it applies. The purpose of this example that I'm going to be covering next time is to show you here a column. So here's the end of the column, right? Here's a column. Here's the beam. So the beam ends here. In this example, I have 3 number 8 bars, top, and some bars at the bottom. From the face of the column, I need to go here, LD and LD on both sides. This is where I have the moment. I need to stop the rebar. I need to extend it for an LD at least on both sides of this interface. So we're gonna try the equation for a straight development length for only LD. You see this equation for L sub D. The problem with L sub D when it comes to the end of the column that this is gonna be much longer than what I can afford, because this column size is only 24 inch. If I'd like to go with the L sub D that I just calculated out in this example, I'm gonna be in trouble. I can just show you here for quick till we discuss in details next time. It shows here 53 inches. So this L sub D is gonna be 53 inches. Meaning the bar is gonna be sticking outside of the concrete column. Let's say this is gonna be like the end. Here's the end of the building. This is gonna be outside of the building. So it's gonna be trouble. I mean, I cannot make it this way. This is gonna be big trouble. That this is gonna be sticking out 24 inch. And the solution to it, either they're gonna be extending the beam outside of the building, which doesn't make any sense, or convert this into a hook. So I'm gonna provide here a hook. Now, if you ask anyone construction, would you prefer to use a hook or a straight length? Straight velvet length. What do you guys think their answer is gonna be? Which one is easier for them?
90-degree.
Do you mean that if they just leave the bar as is, as a straight, isn't this easier in general?
Oh yeah, the straight one is easier.
Yeah, in general, right? So if you ask him to put a hook, you need to have a good reason for it. Otherwise, you just make him here spend some time to give you a hook. So the preference here is to keep it straight, but you cannot. It's gonna be much now more work because you're gonna be extending the beam outside of the building, right? Which you cannot do physically. I mean, let's say here's a property line, right? Or you cannot afford to have 2-foot pieces sticking out of the building this way. It's gonna look very ugly. In a case like this, you'll have to put a hook. I guess I'm gonna stop here and see you next time. Hang around if you have any questions. Otherwise, please sign off or sign out.